day everyone. In this video, I'm going to discuss another example in finding the accumulation points of the given set to further illustrate the concept. Now in this example, we let here x be equal to the set with elements A, B, and C. So we have here, let's consider I. As you remember, I is the indiscrete topology with members only x and empty. Now let's try to consider a set A with elements only A. Now to find the accumulation point of A, we will use the definition in which this condition rather, we have the deleted neighborhood of a point P and then intersection A should not be empty. Now in this case, since we know that our P here, our P must be in X. It's not in A only in the given set A, but we will test it for all points in X. So first, let us try point A. So point A here, say P is equal to A. So again, we will get the open sets containing A. Now as you can see, because we only have this topology here, the indiscrete topology, now the open set containing A is X only. So we only need to test it for an open set X only. So, kumbaga, this is our G in our definition, si X. So we have here the deleted neighborhood, X of A, intersection here, A. So we know that X minus set A is set BC. And then intersection into A, so of course it is empty. So the condition is not satisfied, therefore we can say that A is not a limit point of the set A. Now to test again for P equals B or point P, we will get again the open set containing B, and we know that it is X only. So again, we have here X minus the set B is the set AC, and then intersection to set A is not empty. So since we only have X only ang open set containing B, and it satisfies the condition, therefore we can say that B is a limit point of A. Then for C, still the same process, and we have shown here that the condition is satisfied. So we can say that the C is a limit point of A. Therefore, in the given set, the derived set of A is equal to the set with elements B and C. Okay, what about if we are going to consider another set A wherein it is also a singleton set? Say for example, set A is the set with element B only. So what do you think is the derived set? Now as you observed here, because our set A is a singleton set, so if we are going to get the deleted neighborhood of A, so A is not here in the set, because we are going to get the intersection of that set, A singleton, it is always empty. So if this is B, so B here, so this becomes AC. And then B here, of course, it is always empty. Therefore, the element in the singleton set is not part of the derived set. Then if we are going to take the complement of the element here, of course, the condition is always satisfied. Hence, for any singleton set A, say we have here A with element P, then the derived set of A is just the complement of the set A. So where P is in X. Now, let's have another example. Let us consider B, set B, with is the set with elements A and B. Now, let us try to recall here that X is a set with elements A, B, and C. And our topology here is a collection of sets X and empty only. Now, let's to determine the accumulation point or the limit point of the given set, we will test all the elements of X here. So let's start first element A. So let's have here P equals A. And then with this condition here, we have X as our G, an open set containing A, is X only. So we will only test this one. So X minus set A and then intersection to set P is equal to, of course, this X deleted neighborhood of A is the set BC. Intersection it with B, so the intersection is set B. And this is not empty. The condition is satisfied, therefore we can say that A is a limit point of the set B. Now for B, we have this, and this deleted neighborhood of B is the set AC. Intersection it with set B, of course it is not empty. So again, we only test this one because the open set containing B is X only, because we only have this topology here, the indiscrete topology. Therefore, B is a limit point of set B. And then for C, the same thing. The intersection is not empty, so C is a limit point of the set B. So we have tested all the elements of X, and we have found out that all the elements of X are limit points of the set B. Therefore, the derived set of B is equal to X. So, in general, if a set contains two or more points, then the derived set of that given set is equal to X. Accordingly, the derived set of any subset A of X is this. If the set is empty, then the derived set of A is empty. And then if A is a singleton set, so its derived set is the complement of the set. And if A contains two or more points, then the derived set of A is the set X. So this is true for an indiscrete topological space only. Okay? So, we're done. In my next video, I'm going to discuss closed sets.